Welcome to everyone to this Antarctic Science David Walton Memorial Lecture as part of the SCAR Open Science Conference. My name is Mike Bentley and I chair the board of the charity that owns the journal Antarctic Science. This is a journal that publishes on all aspects of Antarctic research and very much welcomes any new submissions or inquiries for special issues, including where some of you may be running sessions at SCAR or other Antarctic meetings. And our new chief editor is Pete Convey, is very pleased to hear from anyone about papers or special issues, and the email is here. Some of you may know this journal through our bursary scheme or through the sponsored lectures that we run at SCAR meetings. The charity that owns the journal exists to ensure that all of the surplus from journal publishing goes towards supporting Antarctic scientists, and particularly early career Antarctic scientists. And so all the surplus each year goes into bursaries or small grants to early career Antarctic researchers. We award these each year. We sponsor lectures, and we also support the Association of Polar Early Career Researchers. So if you're an early career researcher or perhaps a PhD supervisor, I'd urge you to look at our website for the bursaries, which I've put here. Next slide, please. The lecture today, we've sponsored an Antarctic science lecture for many years, but with the agreement of SCAR, we've now changed that to the Antarctic Science David Walton Memorial Lecture. And that's named in memory of Professor David Walton. David founded the Antarctic Science Journal in 1989 and set up the charity right from the outset. He wanted the proceeds of publication to go towards promoting Antarctic science and Antarctic scientists. And very sadly, David died suddenly last year. And with the support of SCAR, we have renamed this sponsored lecture in his memory. Many of you will know David. He was highly active in Antarctic science matters and in SCAR indeed for many decades, particularly around the Committee for Environmental Protection in the Antarctic Treaty System. And he's actually lead author on the history of SCAR, published in SCAR's 60th anniversary year. David's own research was in plant ecology, but I think one of the things he was most well known for was his knowledge of Antarctic science across a whole range of disciplines, including into social sciences and the arts, where he was a great champion of both those areas of Antarctic science and interest. And he was awarded the SCAR Medal for International Coordination in 2006. Next slide, please. So I'm delighted to introduce the speaker for the Antarctic Science David Walton Memorial Lecture in 2020, and that's Professor Nerilie Abram from ANU. Nerilie studied at the University of Sydney and then at the Australian National University, where she first started with using fossil corals to reconstruct tropical climate variability. After her PhD in 2004, she moved to the British Antarctic Survey in Cambridge as an ice core scientist, where she initially focused on developing sea ice reconstructions and later worked on the James Ross Island Ice Core project. In 2011, she was awarded a fellowship to return to Australia, and since then she spread her research efforts between reconstructing tropical climate variability and Antarctic climate variability, including as an ARC Future Fellow, a very prestigious fellowship she held for some years. She's also led a number of community reconstruction projects as part of the Pages 2K network that many of you will know. And she's now Chief Investigator of the Australian Centre of Excellence for Climate Extremes, and also for the newly funded Centre for Excellence in Antarctic Science. She's one of the chief investigators. She was a coordinating lead author on the recent IPCC special report on the ocean and cryosphere in a changing climate. We're so pleased that Nerilie agreed to be this year's speaker, including with the troubles. I'm glad that Nerilie, you're still able to do this, even though we're not able to join you in person. And in a moment, I'm going to hand over to Nerilie. I'd ask you to please use the Q&A box on the on-air portal if you've got any questions, and we'll come to those after Nerilie's talk. But it's an enormous pleasure to hand over to Nerilie, who's going to speak on discovering Antarctic's climate secrets. So over to you, Nerilie. Thank you very much.
Hello, thank you for joining us online today, and thank you to the organising committee for the invitation to give the David Walton Memorial Lecture. What I want to do today is to highlight some recent work showing Antarctica's place in the climate system. Before I get to that, I thought that I would start with this lovely image from Hobart, where we should have all been meeting this week. I know it was a really tough decision for SCAR and for the local organising committee to cancel this meeting. And until we're able to meet in person again, I'm grateful that we can use technology instead. Now, as idyllic as this image of Hobart is, before the pandemic turned the world upside down, Australia was already facing a disaster on an unimaginable scale in what's been termed our Black Summer. These fires burnt for many months with a scale and a ferocity far beyond any other fire season. So while images like this inferno seem very far removed from the typically icy pictures that we associate with Antarctica, towards the end of today's talk, I'd like to show you how Antarctica actually was part of this story that unfolded in Australia last summer. If you had been in Hobart for SCAR, over the past couple of weeks, you would have seen news stories of these houses that are falling towards the sea along the east coast of Australia. These high sea level events that cause damage like this also have a connection to Antarctica through rising global sea level. On Australia's east coast, high sea level events that were previously a once in a century event are expected to occur roughly every year by around 2040. So that's just 20 years from now. That was one of the findings from the recent IPCC report on the ocean and the cryosphere in a changing climate. I was privileged to be part of the team that wrote this report. And what I'd like to start with today is to use the example of West Antarctica in each of the previous IPCC reports as a nice demonstration of how our knowledge of Antarctica has evolved over the past 30 years. So for the first assessment report, West Antarctica was already mentioned as an area of concern because of the geography of this ice sheet and the marine base that it sits on. But it was also concluded that within the next century, there was not likely to be much of a response of West Antarctica to global warming. By the second assessment report, again, the ice sheets of Greenland and Antarctica were viewed as these very large masses that really weren't expected to change anytime soon. By the third assessment report, the Antarctic ice sheet was actually expected to offset global sea level rise because of extra mass that was being gained across the continent by snowfall. Again, concerns were expressed about the stability of the West Antarctic ice sheet, but again, it was thought that there was very unlikely to be substantial loss of ice and contribution to sea level rise during this century. By 2007, we start to see things changing where we now actually have the observations to show that Greenland and Antarctica were losing ice and contributing to sea level rise. And also information showing that dynamical processes could actually mean that these ice sheets were going to move faster than what we'd previously assumed. By the fifth assessment report, we are now very confident that Greenland and Antarctica have been losing mass, and that if there were to be a collapse of marine-based sectors of the Antarctic ice sheet, that would cause sea level rise substantially above the estimated range given in that report. Then we come to 2019 and the special report on the ocean and cryosphere, where from observations we see that Antarctic ice loss has tripled in the past decade, mostly from West Antarctica. We also see this wording appearing that this may represent the onset of an irreversible ice sheet instability. And we also see in this report that the upper end of estimates of sea level rise have increased by 10% from AR5 just a few years previously, based on a larger than expected contribution to the Antarctic ice sheet. This image is part of figure 1 from the summary for policy makers from that ocean and cryosphere report. This is a figure that takes the observed changes in different elements of the ocean and cryosphere and compares those to projected changes with our choices under a low greenhouse gas emission scenario versus a high greenhouse gas emission scenario. And the reason that I wanted to show you this is because of this panel at the bottom. And as we were preparing this report, governments kept on asking us to visually show the sea level rise information out to 2300. Scientifically, we found that very difficult to be able to do accurately, both in terms of capturing that time scale and capturing the magnitude of changes that we potentially could be facing by 2300 under a high greenhouse gas emission scenario. Nevertheless, when we went to the approval session, we again found that governments were adamant that they wanted this information in this figure as part of the visual. And so we had to find a way to make that work with the IPCC graphics team. And this is the figure that was produced. To me, this is a real kind of slap you in the face kind of figure. But there's a couple of messages that I take away from this. So firstly, there is that message that actually people are listening. Policymakers are wanting this information and wanting to know what the future looks like beyond 2100 in terms of sea level rise. What this also tells me is that Antarctica is going to play a very big role in our future for many centuries to come. So this image here is the most recent image of mass loss from Antarctica from satellite observations. In red colours, you can see the areas that are losing mass, in blue areas that are gaining mass. And immediately you can see that hotspot over West Antarctica, where we know Antarctica is losing mass at an accelerating rate, and the reasons that we are concerned about that. But what I wanted to draw your attention to is just to point out a few places in East Antarctica where we're also seeing evidence that perhaps the ice sheet isn't as stable as we previously thought. So one study published just a week ago from the Wilkes Basin, based on geological evidence, seemed to indicate that there was evidence for the ice sheet margin retreating 700 kilometres inland during MIS 11, so around about 400,000 years ago. So this is from the Wilkes Basin area, so roughly this area here. That would have contributed roughly 3 to 4 metres to sea level rise. Now, one of the reasons why this is quite an interesting finding is because we have these compilations of where we think sea level might have been during MIS 11, and the upper end of that estimate is at 13 metres. Now, 13 metres implies that it can't just be West Antarctica and Greenland in play, and that East Antarctica would also have to be part of the story. And now we have some geological evidence that would suggest that that is a possibility. Over is the Totten Glacier, and behind the Totten Glacier, the Sabrina and Aurora subglacial basins. So we can see this red blotch where Totten is losing mass rapidly at the moment. But here is a different story, probably a little bit more of an optimistic story, in that the sediments beneath the ice sheet appear to suggest that this part of the East Antarctic ice sheet has two quasi-stable configurations. So in the modern configuration, we wouldn't expect the ice sheet to retreat more than about 150 kilometres, contributing up to 0.9 metres to sea level. In a further retreated configuration, the ice sheet looks like it retreated in the past around about 350 kilometres inland from its current position, and that would have contributed more than 2 metres to sea level rise. In this study, it suggested that this retreated configuration may have come into play during the Pliocene, and so contributed to these even higher possible estimates of sea level rise from that very warm period in the past. And finally, this other section where you can see red on the map, this is the area of Denman Glacier, which has recently become of interest because it's the deepest marine-based basin in Antarctica. So it's a very deep and narrow canyon, dropping down to 3.5 kilometres below sea level. And so because of that configuration, it has the potential for rapid and irreversible retreat. And it's estimated to hold around about 1.5 meters of sea level equivalent. And so just showing that profile again. So you can see this typical retrograde bed, and also the evidence that the grounding line is retreating inland. And so potential for rapid changes in that part of East Antarctica. I'd just like to give a quick plug here for the Australian Centre for Excellence in Antarctic Science. This is one of two major research centres in Antarctic science that have recently been funded in Australia. This centre is led by Matt King out of the University of Tasmania. And over the coming years, we'll be looking at the East Antarctic ice sheet and trying to understand which parts are particularly vulnerable in a warming climate and how quickly they may change in the future. This is where I would love to have more time to be able to go into some of the recent work that's been published. But what I wanted to put these up here for is just to highlight that if we want to know about how the Antarctic ice sheet is going to change in the future, we need to understand more than just the ice. We need to be understanding how that ice sheet is interacting with the ocean, is interacting with the atmosphere, and with the ground beneath it, and the ways in which those interactions could either amplify how quickly the ice sheets will change in the future, or in some cases where there's potential for mechanisms that could slow the changes into the future. Now I wanted to come to this review article, which summarizes a common problem that Antarctic scientists face, and that is in the short data sets that we're working with. So the working title of this review article when we were preparing it was 36 years isn't enough. 36 years referring to the number of years that we had at that time of satellite data that gave us good coverage across Antarctica. We could update that now to be 41 years isn't enough, and it would be equally true. But what we have in those 41 years are observed trends that don't necessarily agree well with the trends that climate models would tell us are expected across Antarctica. And we see this type of observational data compared to model data divergence in Antarctic surface air temperature trends, but also in Antarctic sea ice and sea surface temperature. And again, studies that I don't have time to go into profiling in detail, but what I wanted to show with these is just the way over the past few years we've been learning more about this decadal to multi-decadal variability that we see in the atmosphere and in the ocean. And how, if we want to understand the trends and often the perplexing trends that we're seeing in some parts of Antarctica, then we need to really understand what's going on with this variability and how, again, how Antarctica links beyond just the Antarctic system and into the full climate system. So this brings us to where paleoclimate information can start to help us to provide a longer perspective than what we're able to get with our short observational records. What I'm showing here are the regional temperature reconstructions that were produced for different continental areas and tropical ocean areas as part of the Pages 2K network. And the analysis that's been done on these temperature reconstructions is to look at when do we see evidence for the onset of sustained and significant warming in each of these regions. And what we can see when we do this analysis is that across the Northern Hemisphere and the tropical oceans, the onset of the sustained warming that we see through to today began in around about the middle of the 1800s. But as we move into the Southern Hemisphere, we see a delayed onset of warming. And then as we get to Antarctica, in this reconstruction, we don't get the evidence of a sustained and significant warming. That may be something that we're starting to see an emergence in the past couple of decades. And certainly some parts of Antarctica are warming, such as the Antarctic Peninsula and West Antarctica. But in terms of the continental scale and looking across this long time frame, we do see evidence for a very late onset of warming across Antarctica. And one of the reasons why that's quite significant is that it's a result that isn't produced by our climate model simulations. So this is an assessment of those models from the CMIP5, PMIP3 set of simulations shown in blue. And when you look across those models for each of those regions, the models want the onset of warming to be beginning in around about the middle of the 1800s. And that's very different to what we see, particularly for Antarctica. We can also use the paleoclimate records from Antarctica, particularly the ice cores, to look at accumulation trends and put recent changes in accumulation into a much longer context. And this type of work shows that over the past 200 years, there has been an accumulation of mass across the Antarctic ice sheet. Since the 1900s, the quantification of that is that Antarctic snow accumulation probably mitigated around about 10 millimeters of 20th century sea level rise. The other thing that we can see in this analysis are quite distinct spatial patterns in changes in accumulation. And those patterns are related to the effects of the southern annular mode. So this is a reconstruction of the southern annular mode in summer over the last 1,000 years. And by using reconstructions like this, we can start to put into context those strong changes that we've observed, particularly at what you can see here in the Marshall SAM index, where we see this strong positive trend in summer. And when we put this in the context of variability over the last 1,000 years, we said there is a lot of natural variability of the southern annular mode, but those recent trends have moved us to the most positive value of the summer SAM index over at least the last 1,000 years. We see the same in other reconstructions of the summer SAM index and also in reconstructions of the mean annual SAM index. But those of you with keen eyes will have also seen that over the past couple of decades, that positive trend in the summer SAM has eased off or paused. And this was work that was published earlier this year, showing that this pause was the result of the success of the Montreal Protocol. And this is what we would expect based on modeling studies, that as the Montreal Protocol comes into effect and we start to see ozone recovery, then we would expect that positive trend in the summer SAM to ease off. But we do expect that trend to continue in the longer term because of ongoing greenhouse forcing. Other interesting work that's recently been published related to the Montreal Protocol shows the effect that that's also had in terms of avoiding some of the warming that we would have seen otherwise. And this study quantified that by 2050, we would have expected around about 25% more warming under a high emission scenario if we hadn't had the Montreal Protocol. So again, part of a good news story that we can actually make changes that have a positive impact on the climate. Right, so just to tie this back to where we started in here, and I wanted to take us back to the summer that Australia experienced in 2019, 2020, and why we had such a disastrous fire season. So what I'm showing here is the maximum temperature anomaly in southeastern Australia and the rainfall anomaly in southeastern Australia. You can also see shaded on here on the precipitation graph periods of time when we had major droughts in southeast Australia, and the dots show where we've had large forest fires that burned more than 500,000 hectares. So what you can see clearly is the strong warming trends that we see over southeastern Australia, similar to what is seen over many parts of the world. But we could also see that the recent years have been particularly dry, and over the past 20 years, 15 have had below average rainfall in Southeast Australia. If we were to break that down and look just at the cool season rainfall, it becomes 18 out of the last 20 years have had below average rainfall, and the accumulated rainfall deficit is the largest on record. So 2019 was Australia's hottest and driest year on record. That was both in terms of Australia as a whole, but also in terms of Southeast Australia, and that's the data that's shown here. And as the climate has become hotter and drier in Southeast Australia, we've seen forest fires, large forest fires occurring more and more often. And just to show you spatially what that rainfall anomaly looks like, because there is a lot of year-to-year variability in rainfall, but spatially the pattern that we see looking at cool season rainfall, and cool season being the main rainfall season for southern parts of Australia, is parts of southwest Western Australia showing the lowest rainfall on record over the past 20 years. And large parts of southeastern Australia also showing rainfall that's been very much below average or lowest on record. And this drying trend in the cool season in Australia has been related to the positive trend in the southern annular mode. And what that is doing is drawing the storm tracks away from Australia, so that the frontal activity that would normally bring rain during the autumn and the winter is now no longer delivering rain, particularly to southwest Australia, but also to southeastern Australia as well. But those long-term trends in the southern annular mode aren't the only part of the story in terms of what happened in Australia in 2019 and the role that Antarctica played. Because what we saw in the spring of 2019 was this very rare sudden stratospheric warming event develop over Antarctica. These events occur commonly in the Northern Hemisphere, but they're quite uncommon in the Southern Hemisphere. And the event that we saw in 2019 was quite extreme. Around about the same time that this event developed, Lim also published this work showing the effect that past weakenings of the stratospheric polar vortex over Antarctica have on Australian climate. And you can see when we have years with these unusual climate anomalies going on, then we tend to have hot and dry conditions in eastern Australia. So the impact of the southern annular mode on Australian climate, it differs by season. And so in the summertime, the spring and the summer, when we have a negative southern annular mode, which was the consequence of this sudden stratospheric warming, what we see is increased airflow being drawn across the interior of Australia towards the eastern states. And so it's drawing hot and dry air from the desert regions in the centre of Australia towards the east coast, and we have drier than normal conditions. That didn't happen in isolation in 2019 because we also had a very strong positive Indian Ocean dipole event in the tropical Indian Ocean. So with this event, we saw cooler than usual waters around Indonesia to the northwest of Australia. And when we have that climate situation set up, it cuts off one of our important sources of moisture. And so the combination of this climate variability meant that we had increased airflow from the continent towards the east coast, but that airflow was drier and hotter than it would normally be. So combined with those long-term trends, plus this variability, we were set up for that extreme hot and extreme dry conditions that drove the fires in Southeast Australia in 2019. Thank you again for joining for the lecture today, and thank you again to the organisers for the invitation. I hope that it's shown you that we've come a long way in terms of understanding Antarctica and its place in the climate system, and that we still have a lot to learn, and that will have impacts, not just in Antarctica, but for how climate change plays out across the world. Thank you.
Thank you very much, Nerilie. Thank you indeed. Really interesting to see those links between Antarctica and the southern continents, and of course, seeing your world of the tropics also influencing as well. Nerilie, we already have some questions, so I'm looking on the on-air portal. Please do use the Q&A box, and we've got some time for these. So I'm going to go through these, Nerilie. With the first one is, what are the main links between Antarctic climate change and human well-being?
Yeah, so I think that there are multiple links, and in different areas. So there's the obvious one where we're losing ice from Antarctica, and that has an impact on sea level. We have a huge proportion of our population lives in coastal areas, with recent studies sort of suggesting that it's actually more people there than what we'd previously thought. And often those communities that are at risk from rising sea levels are also communities that are some of the least able to actually respond to those challenges, and in many cases have also been very have not contributed much to the overall climate change problem either. So that's the obvious one. I've spoke at the end there about sort of the impacts on southern hemisphere continents, using Australia as an example because it's obviously close to my heart. But the effects that changes in Antarctica have on rainfall, not just for Australia but for all of the southern hemisphere continents, and particularly in sort of pushing the dry mid-latitude areas sort of further south, and that's causing problems in terms of the ability of those populations to have access to fresh water, and also for being able to produce the food that they rely on in those cropping areas. The other aspects are what happens in Antarctica is going to very much affect how quickly climate change plays out across the world, both in terms of the feedbacks that we have in terms of the Southern Ocean and how much carbon it is able to absorb, and also the effect of sea ice on how much of that sun's energy we're able to reflect. And if we do have a dramatic decrease in sea ice, we could start to see much more of the changes like we see in the Arctic, with that amplification of warming because of the loss of sea ice. Obviously, Antarctica is also very important for its fisheries, and that's something that has the potential to have an impact throughout the world. But then beyond any of that sort of scientific information, and I probably don't have to really sort of sell this to the people here who all have a passion for Antarctica, but I think Antarctica has such an intrinsic value beyond just what it does for our climate system, but also just knowing that we have that wilderness, that sort of untouched part of the planet that we're changing profoundly, I think holds a lot of worth, and that we shouldn't give that up lightly.
Thanks, Nerilie. There's a question that's getting a lot of interest here, which is, what are the most important observational measurements we should be making to reduce uncertainty over the sea level rise projection from Antarctica? So what measurements do we need to reduce sea level rise uncertainty?
So I think we need a whole range of measurements, and this is where the interaction of the ice sheet with the atmosphere and the ocean and the bedrock beneath all become very important. Some of the things that I would say are particular areas of uncertainty where getting more measurements will help us to figure out how we develop those sea level rise projections and bring the uncertainty down. Some of those would be looking in detail, taking very detailed measurements of the ocean close to the ice sheet and underneath the ice shelves that surround the ice sheet. We have seen, if we take global scale climate models and we look at the effect of ocean warming coming up underneath the ice shelves and the ice sheet, we get a very different response in a low resolution global scale model as opposed to a model that has a much higher resolution. And so that has a really big potential if those global models that we're using for our sea level rise projections don't actually capture accurately the amount of warming, the amount of ocean warming that the ice sheets and shelves are going to be exposed to. That's going to change how quickly those ice sheets change in our projections. I'd also say that the snow accumulation patterns over Antarctica are something that's very important to try and nail down a lot more. And we still see in the scientific literature differences in studies about whether East Antarctica is contributing to global sea level rise, or if it's still kind of a net zero at the moment. And part of that is the trying to understand East Antarctica is a very big place. It doesn't have a lot of year-to-year, year-on-year snow accumulation over much of the East Antarctic plateau. And so that means that if we need to really sort of get those uncertainties down, otherwise it can have quite a large effect on sort of whether East Antarctica is contributing to sea level rise, or if we are seeing sort of what's being lost at the coast being offset by accumulation over the plateau area.
Thanks, Nerilie. Another question, you touched on this briefly, but somebody's asking, how does ozone depletion impact on the southern annular mode? What influence might we expect in future projections for Antarctic climate? So I guess this is about the role of ozone depletion in climate.
Yeah. So the ozone depletion has meant that we see a cooling at the surface over Antarctica in the atmosphere. And what that does is to increase the difference in temperature between the mid-latitudes and Antarctica in the spring and the summer, particularly when we have sunlight over Antarctica and we have that ozone depletion in play. And when we increase that temperature gradient, what we're also doing then is to increase the strength of the westerly winds that are traveling around the Southern Ocean, leading to a positive trend in the summer SAM. So that's one part of the story, but the southern annular mode is also forced by greenhouse gases, and that's an effect that we see throughout the year. So in terms of moving forward, what do we expect? So we would expect that the positive trend in the winter southern annular mode will probably continue into the future. At the moment for the summer SAM, because of the success of the Montreal Protocol and starting to see recovery of ozone over Antarctica, we've kind of got a trade-off between that ozone recovery and greenhouse forcing. And so we see that leveling off, the plateauing of the positive trend. But looking sort of further into the future, at some point we do expect the greenhouse gas contribution to continue. I think one thing that's probably important to point out in terms of the southern annular mode, though, is that there are some studies that, some model-based studies that suggest that this is a transient response to climate warming. And so it's a response that once we get to a point where we can stabilize temperature, then we actually start to see recovery of the southern annular mode. And importantly for those mid-latitude continents that are currently losing rainfall because of the positive trends, that's something where we can actually see a relatively rapid response for that potential for that rainfall to come back.
Thanks. Question, it's close to my heart as well. In terms of paleo research, what regions or timeframes should we be focusing on to best help with future predictions?
Oh, that's a good one. And I don't think there's one answer to that. I mean, I spend a lot of my time looking at the last 1,000 years because I want to understand that year-to-year variability and be able to put into context the rapid changes that we see now, or in Antarctica, when do we expect some of those changes to start being seen? So I think that that's a really important time period for giving context, and particularly for Antarctica, because we have large multi-decadal variability. Having that 1,000-year, 2,000-year timescale is really important for giving us context there. But at the same time, the future that we're heading to is dramatically different to any sort of climate that we've seen over a very long time period. And so I think that we do also need to have that deep time paleo looking over glacial to interglacial cycles so that we can start to understand which parts of Antarctica do we expect to to change, how quickly do different parts of Antarctica change in a warming climate, because we're already at 1 degree of global warming, and depending on the choices that we make for the future, by the end of this century, we could be at 2 degrees, or we could be at a lot more than that.
Thanks. Somebody's asking about the use of historical records. So is there any way to confirm modelling reconstruction through historical records of sea ice, such as whaling observations or older scientific studies of Antarctica? So I guess the question is, what role do historical records have in testing some of our modelling?
Yeah, I think it's a fascinating area of research, and I think it's great to see that there are programs like the ACRE project that are trying to recover this information where we already have measurements, but they're just not part of what is freely available for scientists to use. So I think that they are very, very important for giving some of that longer term context, not just for testing the models, but also for ground truthing the interpretations that we make from paleoclimate data as well. So the historical data sets give us another one of these sort of independent lines of evidence that we can use to see, like, how well are we actually capturing this system. I think that we also have to bear in mind that historical records will have their own biases. So for example, things like using the whaling records for reconstructing sea ice, we know that there's some issues there in terms of when whaling changed from different species, then they're located at, the whaling ships were going to different parts of the marginal ice zone. And also whether sort of those ships were really sort of going as close to the sea ice as what we would interpret them. So I think that there's a huge place for that, and a really exciting area to see develop. Thanks.
So Nerilie, we've got a couple more questions on the ice sheet, and then I'm going to let you finish with a plug for ACS. So on the ice sheet, somebody's asking about MIS 11, marine isotope stage 11. You talked about more than 13 meters, and the question is, does this need more than the West Antarctic ice sheet to melt? Do you need the all or part of East Antarctic ice sheet melted too?
Yeah, so that high end of the estimates, and I will say that it is an estimated range. So sea level probably somewhere between 6 meters and 13 meters higher during MIS 11. That's quite significant because during that period of time, it's estimated that the global temperature was around about 1 to 2 degrees warmer than present day. So really in the place where we've found ourselves now, and going forward, and potentially sort of, yeah, moving into even warmer temperatures quite rapidly this century as well. So it's important to understand what those sea levels were and where it came from. If it is 13 meters of sea level rise during MIS 11, then it probably means that, yes, we can't just do that with Greenland and West Antarctica, and that East Antarctica had to have contributed as well. I think that would seem like quite a reasonable expectation, given that we're already seeing some evidence that there could be parts of East Antarctica that are susceptible, like Denman Glacier with its marine base. We're seeing parts of Tottenham Glacier changing quite rapidly at the moment as well. But the evidence that I pointed to there actually comes from Wilkes Basin, which is based on calcites that were accumulated, and looking at the radiometric decay within those samples, which suggested that they were formed 400,000 years ago from marine sourced water. So that's where that estimate comes from, that there is that evidence for substantial amounts of ice loss from Wilkes Basin during MIS 11. So I think it's a really exciting new technique. I think there's still a lot of work to do to see is that really sort of a robust result, but certainly a very exciting area to sort of explore as well.
Yeah, absolutely. And I think there's a lot of work going on to tighten up the global sea level estimates at the same time that the individual ice sheet estimates are being tightened up. So last one on the ice sheet, and then I'll give you one final question after that. Somebody's asking about the tipping point for the irreversible collapse of the West Antarctic ice sheet. We're often hearing that lies between 1.5 and 2 degrees. Are we likely to be able to pinpoint this more precisely in the coming years?
I'd like to hope that we could, because it's something that is fundamentally important for planning going into the future. But I would say that I'm probably not optimistic about whether we actually can really pinpoint where those tipping points lie. And I guess that's one of the things with tipping points, is that they're easy to see in hindsight, but pretty difficult to predict where they actually are. So I think just the fact that there is the potential for a tipping point there, and we do see, including in the most recent IPCC report, that Ocean and Cryosphere report, that there is more attention being given to the potential that we do have these high impact end member sort of possibilities that we can't rule out. It's unlikely that some of those high sea level rise estimates would happen, but it's still a possibility. And the fact that it's a possibility means that we actually have to take that seriously.
Okay. And then final question, Nerilie. During your talk, you mentioned the newly funded Antarctic Centre for Excellence in Antarctic Science. And we have a question about how will this new centre collaborate with or differ from current Antarctic research groups? So if you'd like to give a brief plug to that, and then I'll close the session.
Yeah, so there were two major research centres that were recently funded in Australia on Antarctic science. So there's one centre that's being led by Stephen Chown out of Monash, and that will be looking particularly at Antarctica's environmental future. And then the ASUS centre led by Matt King, that will be focusing particularly on trying to do research that helps to bring down our uncertainty in future sea level rise, focusing particularly on East Antarctica. It will be collaborating with some of the other programs that we have in Australia, also has a number of international partners as well. And I think that's one of the things that makes the Antarctic community such a fun community to be a part of, because none of us can do this on our own. And so that's, I think, part of why we actually have such a strong connection as a community, is because we know that to do this type of work and to work in a place like Antarctica, we need these big networks to be doing really ambitious science. So yeah, stay tuned. So that centre and the other centre will be beginning sort of probably around about the start of next year. So planning is currently underway for really sort of locking down the research programs and the field programs associated with them. Thank you.
That's great. Thanks, Nerilie. And that's a nice look forward ahead to, as you say, an unusually collaborative and fun community that we're part of. And like everyone else, very sorry that we can't be meeting up in Hobart, but I look forward to when we can. So it just remains for me then to thank the 200 plus attendees for giving some of their time to come and listen to hearing about Antarctic climate secrets. And of course, many thanks to you, Nerilie, for giving this fascinating talk, real insight into the very up-to-date latest findings in how climate variability can actually affect the southern continents as well. So thank you, Nerilie. And I would ask people look around the site, go to other live sessions, have a look at the abstracts and the posters and so on. But otherwise, I'm closing this session now. So thanks very much.